Hello. Have you ever wondered about our place in the big wide universe? Let's talk about it today. Our very first rendezvous with the sky is something like this. Maybe even before we can recite the rhyme, Twinkle, Twinkle, Little Star. But when we grow up, our perception of the sky changes. To most of us, the night sky will look like this from a good side. On a cloudless night, when the moon is not high up in the sky and there are no city lights to inhibit the view. We can see all this and much more in the night sky, and we have done that forever. And this is the most beautiful thing about astronomy. It is free and accessible to everyone. And that is why there are so many stories about the sky and the celestial objects in every culture of the world. But most of what we perceive as common knowledge in astronomy is as recent as only a century or so old. Imagine this. When your grandparents were born around the 1920s, we were still debating the size of the universe. How big is it? Is it only composed of objects we see, or does it extend beyond them? Many such questions in astronomy have been answered only in the last few decades. For instance, this is a tiny patch of the sky where nothing is visible to the naked eye. But a telescope placed in space when staring into an ordinary patch of the sky can see all of these objects. This is the Hubble Deep Field. Every single point of light in this image is a galaxy except these two stars, which are in our own galaxy. The light from these galaxies has traveled for billions of years before reaching our eyes. Looking at such a detailed image of the sky is like looking deep into the history of space and time. This image includes some of the oldest galaxies ever observed by mankind. From times when the universe was much smaller than its present size, and yet it was captured by a telescope sent into the orbit in the 1990s. Our universe is full of different types of galaxies, but broadly speaking, they can be classified into spirals and ellipticals. Sometimes two galaxies can interact with each other to form interesting looking systems, leading to formation of even bigger galaxies. We live in a spiral galaxy called the Milky Way. Our solar system, orbiting the sun, is in a spiral arm, around 8 kiloparsec away from the center of the galaxy. The image on the right is a scientific image based on the observations of our neighborhood and other galaxies in the universe. Since we are in a spiral arm, we see a lot of dust in one part of the sky and stars in other directions. This is what I mean. This is the Milky Way as observed from the Cerro Tololo Inter-American Observatory, the CTIO in Chile. In fact, the skies in the southern hemisphere are very different from the northern hemisphere because of these two fuzzy things. These are the Magellanic Clouds, two of the many satellite galaxies of the Milky Way. They are orbiting our galaxy just like the moon orbits the Earth. Ferdinand Magellan was a Portuguese explorer. During his voyages, he noticed and recorded in his memoirs that there are two cloud like objects in the sky which are visible night after night after night. They were thus named after him as the Magellanic Clouds. Besides the Magellanic Clouds, there are several other small galaxies orbiting the Milky Way. In fact, all of these galaxies, along with two other large galaxies and their satellites, form a gravitationally bound system we now call the local group. The local group comprises more than 120 dwarf galaxies and three massive galaxies: our own Milky Way, M31 or the Andromeda, and M33, the Triangulum galaxy. Milky Way and Andromeda are around 1 megaparsec away from each other. This is the typical distance between large galaxies in the universe. Andromeda is also a spiral galaxy, slightly bigger than the Milky Way, and it is coming towards us with a speed of 125 kilometers per second. Models suggest that Milky Way and Andromeda will have a head-on collision in about 4 billion years' time. But before going ahead, let's take an overview of the universe at large. The large-scale distribution of all matter in the universe, visible and invisible, is filamentary. Galaxies are distributed on this web just like dewdrops on a spider's web on winter mornings. The distribution requires us to define the environment of a galaxy in terms of the projected number density of galaxies surrounding it. And therefore, the environment can be categorized into three major components. The clusters or groups of galaxies are the densest regions in space, with hundreds of thousands of galaxies bound together by gravity. The intermediately dense environments are found on filamentary structures crossing the clusters and surrounding the vast empty regions devoid of matter known as voids. If we zoom out further away from the Milky Way, we start seeing this large-scale filamentary structure surrounding the local group. The simulation that you see here is around 9 megaparsec across and shows that the local group lies on the outskirts of a rich cluster of galaxies known as the Virgo cluster. The Virgo cluster is a large congregation of thousands of galaxies. It is at a distance of around 16 megaparsec from the Milky Way. Due to its large size and relatively nearby distance to us, it has a large angular size in the sky. The image on the right shows the galaxies in the Virgo cluster along with the filamentary distribution of galaxies and voids surrounding it. But the Virgo cluster is only the gravitational center of an even larger system called the Virgo supercluster. The Virgo supercluster comprises of almost 100 small and large galaxy groups, including our local group, and spans more than 30 megaparsec across. A supercluster is a distribution of galaxy groups, clusters, and filaments. It is believed that there are around 10 million superclusters in the observable universe. The image that you see here on the left is a slice cut out of the 3D universe. Every single point here is a galaxy, the distance to which has been measured using the spectrum of the galaxy by the Sloan Digital Sky Survey. In this image, we are at the center, and as far as we can see, the distribution of galaxies in the universe is filamentary, and several large concentrations, such as these superclusters, become evident. In fact, a team of astronomers mapping the galaxies in the local universe found that the Virgo supercluster itself is a component of an even larger congregation of intricate system of galaxies, which was named the Laniakea supercluster. The Laniakea extends more than 150 megaparsec across, with a mass estimated to be 100,000 times that of the Milky Way. It is home to about 1 million galaxies. The Laniakea itself is composed of 4 major superclusters: the Virgo supercluster with us in the local group, the Pavo-Indus supercluster, the Southern supercluster, and the Centaurus supercluster. Before we move forward in our exploration of our cosmic neighborhood, let's take a minute to review our understanding of the expansion of the universe. We now know that the universe is expanding, and the analogy used to demonstrate this is that of a cake dough with raisins in it. As the cake dough expands, the distance between the nuts increases because of the expanding dough. Similarly, as the space expands, the galaxies appear to move away from each other, as was shown by Edwin Hubble. However, the problem with this analogy is that even though the raisins in the dough cannot move on their own, the galaxies can interact with each other gravitationally. Hubble used the 100-inch telescope at the Mount Wilson Observatory in California to take spectra of galaxies. And when Edwin Hubble plotted the velocities obtained from these spectra as a function of the distance to the galaxies, he changed the course of our understanding of the universe forever. Edwin Hubble found that most galaxies in the universe are receding away from each other. Such a motion of galaxies with the space is called the Hubble flow. Unless we think we are at the center of the universe, if such a law exists, then it means that the universe is expanding. Around the same time, the theorists working with the Einstein's theory of relativity found that there are two solutions to the equation governing the universe. So, with the observational evidence presented by Hubble, it became almost certain that we are living in an expanding universe. But the story doesn't really end there. In fact, the Hubble law seems to suggest that the farther away is a galaxy, the faster it is receding away from us. Decades of effort were put into exploring this idea. And finally, precise distance measurements of supernovae in the nearby and distant galaxies confirmed that the universe is indeed not just expanding but accelerating due to the presence of a mysterious component called the dark energy. Sean Perlmutter from the Supernova Cosmology Project, jointly with Adam Rees and Brian Schmidt from the High Z Supernova Search, were awarded the Nobel Prize in Physics in the year 2011 for this discovery. But notice that all the galaxies in the Hubble diagram do not line up along the straight line. The slope of this line fitted to the data gives the rate of expansion of the universe at any given time. This is called the Hubble constant. The departures from the straight line are due to the presence of other objects in the vicinity of a galaxy which can influence its motion. For instance, the Milky Way and Andromeda are coming close to each other because the gravitational attraction between them is stronger than the Hubble flow, ripping them apart. Such motions of a galaxy is called its peculiar velocity. In other words, peculiar velocity is the motion of a galaxy apart from the Hubble flow caused by other matter surrounding it. Measurements of peculiar velocity are therefore a great tool for mapping the distribution of matter, visible and invisible, in the universe. By measuring the motion of our Milky Way relative to the cosmic microwave background, we have found that we are being pulled towards the constellation of Centaurus with a peculiar velocity of around 600 kilometers per second. However, this mysterious object pulling us lies in the part of the sky called the zone of avoidance, which is obscured by the disk of the Milky Way. Due to the presence of large quantities of dust in the disk, our view of about 20% of the sky is obscured. The dust in this part of the sky does not allow any optical photons to pass through it, and hence astronomers have named it the zone of avoidance. So the mystery of what was causing us to move through the space troubled the astronomers for over 4 decades. It was speculated that our peculiar motion could be due to the position of the Milky Way in the outlying regions of the Virgo cluster. And while it is true that Virgo, with a mass of about 1,000 times that of the Milky Way, is attracting us, it is not massive enough to explain the speed at which we are moving. This puzzle began to unravel in the 1980s when the digitized sky surveys came online and we started to map the large-scale structures in the universe. But advancement in technology brought with it precise measurements and hence issues which further complicated the matters. In the 1980s, it was found that not just us, but around 400 nearby galaxies in the local universe around the Milky Way were also moving in the same direction as us. So whatever this attractor was, this mysterious object or force lurking in the darkness of the zone of avoidance had to be much more massive and stronger than anything we knew at the times. Professor Lyndon Bell and his collaborators suggested that this attractor must be at a distance of 40 to 70 megaparsec from the Milky Way. Given the magnitude of its gravity, strong enough to pull not just us, but most of the galaxies in the local neighborhood, they named it the Great Attractor. The mystery of the Great Attractor puzzled the astronomers for another 2 decades, but the technological advancements in the meantime led to observations of the sky not just in the optical but at other wavelengths as well. The most significant of these in this context are the X-ray observations of galaxy clusters. Being more energetic than optical photons, the X-rays can penetrate through the dust in the disk of the Milky Way galaxy, therefore making it possible to see through it and observe what lies beyond it. Consequently, amongst many other clusters discovered in the zone of avoidance, astronomers also discovered the Norma cluster, or the Abell 3627. Abell 3627 is at a distance of 67 megaparsecs from the Milky Way in the general direction of the Great Attractor. However, astronomers noticed that although it is big and close to the center of the Great Attractor, it was still not massive enough to account for the Milky Way's peculiar velocity. A decade later, improved X-ray observations led to the discovery of more than 200 galaxy clusters in the zone of avoidance. These clusters were discovered by a team of astronomers working on a survey called the Clusters in the Zone of Avoidance, or CISA. Most of these galaxy clusters were previously undetected and many of them were near the Great Attractor. However, the puzzle remained unresolved because just like the Norma cluster, these clusters were also not massive enough to make the Milky Way move with such a high speed. But soon, the CISA team brought another piece of the puzzle to the table. CISA astronomers detected X-ray emission from a massive structure further away in the direction of the Great Attractor. This structure, known as the Shapley supercluster, is composed of more than 25 galaxy clusters marked here in blue. It was discovered by Harlow Shapley in the year 1930. However, its journey to fame began at the turn of the millennium with the advent of technology. This structure, known as the Shapley supercluster, is composed of more than 25 galaxy clusters marked here in blue. It was discovered by Harlow Shapley in the year 1930. However, its journey to fame began at the turn of the millennium with the advent of technology. These are X-ray images of the core of the Shapley supercluster. At a distance of around 200 megaparsec from the Milky Way and a mass equivalent to 10,000 times that of the Milky Way, the Shapley supercluster is one of the largest cosmic structures in the local universe. We now believe that 44% of the peculiar motion of the Milky Way is caused by the galaxies in the Great Attractor region, while the rest of it is due to the Shapley supercluster, which is pulling the Great Attractor along with us in the local group towards it. The Shapley supercluster extends more than 150 megaparsec across and is home to about 1 million galaxies. The final piece of the mystery of the Great Attractor unfolded in the year 2016, when the group of astronomers who had previously discovered the Norma cluster announced the discovery of another structure called the Vela supercluster at a distance of 245 megaparsec from the Milky Way. Around 50 kilometers per second of the peculiar motion of the Milky Way seems to be caused by the Vela supercluster. In effect, this implies that Milky Way's drift through the space against the Hubble flow is a compound effect of the gravitational influence of several structures which seem to have conspired together to create a great cosmic mystery, the mystery of the Great Attractor. And although at present we can observe the Milky Way and its neighboring galaxies drifting towards the Great Attractor, which in turn is gravitating towards the shapely supercluster, there is no way we will ever make it to the gravitational center of the great attractor. There is a strong probability that much before that can happen, the expansion of the universe will overcome the attractive force of gravity and disperse the Laniakea and other superclusters into their constituents, forcing them to become one with the Hubble's law. On galactic scales, the only certainty as of now is that of a collision between the Milky Way and Andromeda, which will happen in about 4 billion years from now. I hope you learned something new today. Do let me know in the comments what other topics would you like me to cover on this channel. I'll see you next week. Until then, take care.